Today we will discuss the propagation of electromagnetic waves in anisotropic medium. Anisotropicity basically means that if a property depends not only on R but also on theta and phi. So if it becomes direction dependent, any property which is direction dependent would be called as anisotropic property. So which would basically, for example, if I say that let's say that density of a material, if a density of a medium is same at all points equidistant from the origin, so if let's say this is the origin and the density is same at all these points on a sphere, then we would say that it is isotropic. The density is isotropic. It could be different at different R, but it should be same at the same value of R. So anisotropic, if it's same, then it would be isotropic. And isotropic and spherically symmetric, they are both basically the same thing. So any property which is direction independent would be called isotropic. If it is not direction independent, if it is depending upon the direction, we would say that it is anisotropic. Okay, so in this discussion we would consider only those media whose electrical properties are direction dependent. So anisotropic with respect to electrical property, not with respect to magnetic property. We would still maintain that the magnetic property is still isotropic, okay, but the electrical properties are not isotropic. So what would that lead to? It would lead to basically that if you know that the relation between the displacement vector and the electric field, it is like this: D is equal to epsilon E. E is the permittivity, that is nothing but the electrical property of the medium. So if E happens to be different in different directions, then obviously this relation would not remain the same. So if the medium is anisotropic, electrically anisotropic, it would basically mean that E epsilon is different in different directions. Okay, let me then open it up by complicating things, because this basically would that mean that in x direction dx is epsilon ex. Okay, so in the x direction it's still E epsilon, in y direction it is epsilon ey, because this vector equation means this only, and dz similarly would be equal to epsilon ez. So all the three have same E, same epsilon. So here it is isotropic. So let me open it up for anisotropicity. So in order to do that, what we would in general assume would be that, let us say that dx, the x component of d, not only depends on ex as this equation, but it depends upon ex also, it depends upon ey also, and depends upon ez also. So let me take the multipliers as exx, call this as exy, and this as ex epsilon x z. So you can see that we can similarly define dy epsilon yx ex epsilon yy ey epsilon yz ez, and dz similarly would be epsilon zx ex epsilon zy ey epsilon zz ez. Now these three, so now we have opened up. Now epsilon is not the same in all directions. Okay, so this becomes anisotropic and electrically anisotropic. Now these three equations can be written in the form of matrix also. It would be dx, dy, dz, like this. Then you have E epsilon xx, epsilon xy, epsilon xz, epsilon yx, epsilon yy, epsilon yz, epsilon zx, epsilon zy, epsilon zz, and then here ex, ey, ez. Okay, this can also be written in tensor form. It is simpler to write in that form, because in that case it would be di equal to epsilon ij ej. Okay, in this tensor form, j coming to any index coming twice basically would mean that it is summation over j, whether you explicitly notation you give it or not. It would mean basically that it is summation over j. So the three equations combined can be written in this simple form in the form of tensor. So di is epsilon ij ej, where I and j over here are basically running over x, y and z. So I equal to x would give us this equation, I equal to y would give us this equation, I equal to z would give us the third equation. J in all the cases would run over x, y and z. So this is the case. Now we have already opened it up. We have assumed that epsilon is not same in all the directions and it is different in all the directions. That is why we have now these many epsilons coming into the equations. But let me instead of the next demand is that what would be the electrical energy? As we know that the electrical energies are defined by half E dot D. Half E dot D. So we would still want the electrical energy to be defined like this only, which means that this would be equal to, in our case now, it would be half. This is Ek dk, because this is dot product, summation over k. But dk can be written in this form, so this would be equal to half summation over Ek as it is. Dk would become epsilon kl dl. This is also summation over L. So this was summation over K. Then in this case summation over K also and L also. So WE would become this. Now what would be then the rate of change of electrical energy? dWE by dt. It would be nothing but half summation over K summation over L. Now you'll have to, because you have Ek and dl both, so you have two terms, Ek epsilon kl dl dot d by dt plus Ek dot epsilon kl dl. Epsilon kl, of course, is a physical property which does not depend upon time. So these are constants with respect to time. So you have differentiation only on dl or Ek. So these are the, so dWe by dt is this. But if you remember, while discussing the Poynting vector, we had seen that dWe by dt, the rate of change of electric field, is nothing but half E dot, sorry, not half, E dot d prime. In the case of when we were studying the Poynting vector, just to remind you about that, we had started with the two curl equations of Maxwell's equation. So del cross E, which happens to be minus del B by del T, and the other equation has del cross H, which happens to be J plus del D by del T. Okay, and what do we do is, to get the equation for Poynting vector, we take a H dot with this, E dot with this, and then do this minus this, which would basically mean that the left hand side would be H dot with del cross E minus E dot with del cross H, which is equal to minus H dot with del B by del T from here, and here it will be minus E dot J minus E dot with del D by del T. So this is nothing but minus E dot J. Now these two were the equations. This is H dot B dot dV by dt plus E dot D dot. And then we have done the analysis and saw that this whole thing is nothing but the rate of change of electromagnetic energy and electrical energy, and this is nothing but the rate of change of electrical energy. So this is where we have taken from, and then so rate of change of electric field is nothing but E dot D. Now if it is so, both are still vectors. These are vectors. Now if this is so, then what is E dot D? D dot, it would be EK and dk dot, which would be EK and dk dot from here, dk dot would become epsilon KL and EL dot, and this is again summation over K and L both, because this was summation over K and this would be summation over K and L both. So what we want is that even if we have chosen we have allowed epsilon to become different directions, we would still want that the earlier definition of rate of change of electrical energy that we had taken like this should still be same as this, which means that these two, the demand is that these should be same, so that our earlier definition of electrical energy remains intact. So when I want these two to be equal, I'll have to write summation over K and summation over L. This side is EK epsilon KL EL dot, which is equal to half summation over KL summation over L, and then EK I've made here also a mistake. This should be EL. Let me take this liberty. Okay, because dk was epsilon KL EL, not DL. So EL dot over here, EK dot over here. So this is EK epsilon KL EL dot plus EK dot epsilon KL and EL. Okay, so now if you compare these two, you can see that EK and EL dot, and here you have half. So if I take this one this side, then I'm writing it. So half epsilon summation over k summation over L, and then what this is half, so it will become minus. So I'm writing this first, ek dot epsilon kl el minus ek epsilon kl el dot. This should be equal to 0. Now the facility that we have over here is that k is also to be summed up, L is also to be summed up, k is also. So these indices are not specific indices, they are running indices, and running indices can always be changed to one form or the other. Okay, so what we do is, let us exchange k and L over in this, not in this one, but only in this one. Okay, so I'm just writing, let me consume half into the 0. So this would be summation over k, summation over L. I'm writing down the first term. So ek dot epsilon kl el. And now let me write down the second term, kl. And let me exchange kl over here. It can be exchanged because both are running indices. So it would become el epsilon, instead of kl it would become lk and ek dot. So if I take epsilon summation of k and summation L out, we can see that ek dot el, so in both of them we have ek dot el. Here you have epsilon kl and here you have epsilon lk equal to 0, which would mean that this can be 0 only when epsilon kl is equal to epsilon lk. And that would do what? This would just tell us that epsilon is a symmetric matrix. Symmetric matrix means earlier the matrix that we had was epsilon xx, xy, xz, yx, yy, yz, zx, zy, zz. So we had basically 9 unknowns to be known. If you want the relation between D and E to be known, then you had no option but to find out what are these values of epsilon. But now since we know that epsilon is symmetric, it would basically mean that this 3 would correspond to these 3. So now the problem would be that epsilon xx, epsilon yy, epsilon zz would be unknown. But if you know only one half from the first xy, xz and yz, then these would be automatically known. So the unknown reduces from 9 to now 6. Okay. If you remember the electric energy, which was half E dot D, now it can be written as, what would be electric energy? It would be half E dot D, which means it would be summation over half summation over Ek dk, and this would be half summation over k, this was summation over k, summation over L, epsilon k, E kl el. Okay, so if you just write down the whole, all the value, all the terms in this equation, you would see I'll just write 2WE would be equal to, now I'm writing down all the terms, K and L both running from X, Y, Z, all of them. So when K and L both are X, so EXX, you'll have EX square, because EX and EX. Similarly, when both are Y, EYY is EY square. When both are Z, epsilon ZZ, EZ square. When one of them is X, the other is Y, then EXY. But epsilon XY would be equal to epsilon YX. So you'll have twice of this. Similarly, twice of YZ, EY, EZ. Similarly, twice of ZX, epsilon ZX, EZ, EX. So this is all electrical energy. Twice of the electrical energy is this form. Now, in mathematics, we know that any symmetric matrix that is like this is symmetric now because of this equation. So this is not symmetric. Any symmetric matrix can be diagonalized. What do we mean by that? Diagonalizing means that these cross terms would be absent in a diagonalized matrix. You will have terms only in the diagonal, and the non-diagonals will become 0, which means that if that happens, then the relation between the electrical energy and this, you'll have these three equations absent. Only these three terms would be there. Only these three terms, because E epsilon xy, this is xz, and yz, all the three, and these three also would vanish and have to term like this only. But what do we mean by diagonalization? Diagonalization basically means that, if you remember, even the ellipse that you have, if I write an equation for the ellipse like this, how do we write? Y x square divided by the a square plus y square by b square equal to 1. This is the equation of ellipse. But this is equation of ellipse only when the semi-major axis and semi-minor axis corresponds to the x and y axis. So in this case, you can see that if I just write x square b square x square plus a square y square equal to a square b square, I can write it like this: a square b square, take common, so b square x square plus a square y square. So this is an expression in which you have x square, you have y square, you don't have xy terms. But the same ellipse, if you try to write that equation of the ellipse for, let us say, another axis like this, then you would see that you'll have terms in xy also present in this equation. So how did we make the term xy vanish? We made that term vanish by aligning the axis, xy axis, with the semi-major and semi-minor axis. Similarly, this happens over here also, that if I choose our x, y and z axis, this is a three-dimensional case. If I choose x, y and z axis in such a way that it corresponds to the semi-major and semi-minor axis of the ellipsoid, this is an equation of ellipsoid, this is called ellipsoid. In general, this is an ellipsoid. So ellipsoid in which you'll have three major axes. An ellipse has only two major axes, one major axis, one minor axis, but two axes. In this case, we'll have 3 axes. And if the 3 axis gets aligned with x, y, and z, then what happens that this becomes diagonalized. And mathematically it can be shown, it can be proved that a symmetric matrix can always be diagonalized, which means that by choosing the x, y, and z axis, you can always make these 3 terms vanish without the loss of generality. We have not done anything, we have just chosen the axis. So by the suitable choice of x, y, and z, we can reduce this to a matrix of this form only: exx, eyy, ezz, and all of these would become 0. So the epsilon matrix would become this. So earlier we started with 9 unknowns, but we saw that if you want to retain the definition of electrical energy, the earlier definition, then we had no choice but to take the matrix symmetric. And once we choose it to be symmetric, then we know that we can always diagonalize it. So the only unknowns are left we are left with are E epsilon xx, epsilon yy, epsilon zz. So instead of xx, eyy, and ez, let me take it as ex, epsilon x, epsilon yy, and epsilon z. This is nothing but epsilon xx, fyy, and epsilon zz. So which means that now this electrical energy 2WE would become, in this diagonalized format, this would become epsilon x, ex square, epsilon y, ey square, plus epsilon z, ez square. So till this point, we have not done any kind of simplification. You must understand that we started with the most generalized format of relation between D and E with 9 unknowns, but we saw that we can do away with all the 6 and we can retain only 3. We'll have now 3 unknowns to be known: epsilon x, epsilon y, epsilon z. So epsilon in the direction of x will be ex, epsilon in the direction of y is this much, epsilon. Now we have 2 choices basically. 3 choices. One is that all the 3 could be different, or what we can consider is that 2 of them same, but the third is different. When all of them are different, we call that as biaxial crystal. Epsilon x, epsilon y, epsilon z, when all are different. The crystal or the anisotropic medium, because anisotropic media generally we get it from in crystals only. So these crystals are known in which epsilon x, epsilon y, epsilon z all are different. They are called biaxial crystals. And when 2 are same, the third is different. Ex is equal to ey, but they are not equal to ez, let's say. Then this is called uniaxial. Crystals. Okay. Now let us move further. Now, so what if, let us say that we have come to this point. Now let's try to analyze, try to see what happens to the Maxwell's equations. Okay. So Maxwell's equations, let's say we all know that there are 4 Maxwell's equations. Del dot T is rho, del dot B is 0. Then you have 2 curled equations. Del cross E is equal to minus del B by del T, and del cross H is equal to J plus del D by del T. Okay, now in this case of anisotropic material, let me take this equation. This equation is that del cross E is equal to minus del B by del T. Now we know that del by del T can be replaced by I omega. So I omega B, and del can be replaced by minus Ik. So minus Ik cross E. K is the propagation vector. Cross E is equal to minus I omega B, and minus I omega B can be written as mu H. Okay, so minus I goes, you have K cross E equal to omega mu H. Okay, so what does this mean? This means that H vector in this case is still perpendicular to K and E. So H vector is, if I call this, let's say H vector, then it would be perpendicular to the plane containing K and E. Okay, so if let's say that this is E, then K, between E and K, you do not know what is the angle, but K and E both would be perpendicular to H, and K cross E is H, so the right hand rule, K cross E would move in the direction of H. If you draw a screw rule, K cross E would be equal to H. So this relation tells you this much. Now if you take the other one, this one, and for simplicity let me take the medium in which J is 0, there is no free current, no net free current, then del cross H would be equal to del D by del T. Del by del T is still I omega D, and del is minus Ik cross H. I goes, and you have K cross H is equal to minus omega D. So what is this telling us? It's telling us that the direction of D is perpendicular to K and H and with a minus sign. So the screw rule will tell us what is the direction of D. So K and H. So K and H, otherwise it would move in this direction, but since it's minus D, so it would be somewhere in this direction, not necessarily in the direction of E, because E and K are not perpendicular. See, we have two relations. One is this, the other is this. This relation is telling us that K and E is a plane and H is perpendicular to that. So H is perpendicular to this. But between K and E, it could be any angle. This relation is telling us what? That K and H, D is perpendicular to K and H. And in the direction of, the minus will tell us exact direction according to the screw rule. So D is in this direction. So in general, D would not be in the direction of E, because K is not necessarily perpendicular to E. Now, but what is S? S, we know the Poynting vector, that is E cross H. So E cross H, if you see, it would be the direction of S. You can work it out and see that this angle would be same as this angle. Okay, so S, E and H is making a trial. S, E and H, all the three are perpendicular to each other. K, D and H are also making a triad in which K, D and H are also perpendicular to each other. So S, E and H, they are making a triad, and K, D and H are also making a, so H is, in both the cases, H is the same, so H is same. So both, all these three is also a triad, and these three are also making a triad. Okay, and so in general we can see over here that D would not be in the same direction as that of E. Now, if it is not so, then what is the direction? What is the direction? So let me take this one. D is equal to minus 1 by omega, and then K cross H, which is equal to minus 1 by omega, and K cross H. H is this. So it is K cross H is 1 by omega mu, and then K cross E, which means minus 1 by omega square mu, and then K cross E, which is equal to minus 1 by omega square mu, and then this can be written as, from vector algebra, is K dot E with K minus K dot K with E. Okay, so D is equal to this much. I can write it as D is equal to, if I consume minus inside, this omega square mu, and then K square E minus K dot E with K. Okay, if let us say that we write K as, K vector as the value, the magnitude K into, let us say, the vector in the direction, unit vector in the direction K as N, then that way I can write this as minus omega square mu, 1 by omega square mu. This would K square would become K square only, so K square common. So we'll have only E over here, minus this would be N dot E and N over here. So this is our D. To understand this equation, this expression basically, let's look at the diagram. D and E, now we know that they are not in the same direction. Just as this, let me write it slightly magnified way. D is, let us say, this side, and E is this side. This is E, this is D. Now what does this relation tell you? This is E, the vector E minus how much? Minus the projection of E in the direction of K. N is the unit vector in the direction of K. So E in the direction of K, and this is, so this basically means that this is E. If you take the component of E in the direction of K, K is perpendicular to D. So K is perpendicular to D. So K is this. So the equation that you have, E minus N dot E N is what? This is nothing but E is this vector, and this is how much? This is the projection of E on K vector, and if you take, so this magnitude is N dot E is nothing but this much, and in the direction of N, so this is this vector. So E minus of this much would basically mean that it is this much of the vector. If I call that as E perpendicular, this is E this direction, E in the direction of D basically. I can also call this as ED if you so wish. So ED. So this vector is in the direction of D, in the direction perpendicular to K, component of E that much. Okay, but D is not only this much, it is K square by omega square mu into ED, which is this much. So now if I progress further, what I can write is that, let us say that D is equal to K square omega square mu, and then E vector minus N dot E vector with N. Okay. Now if I say that N is what? It is a unit vector in the direction of K. In the direction of K, this is the unit vector N. Let me say that this has the cosine angles as alpha, beta and gamma, which would basically mean that it would be cos alpha I plus cos beta j plus cos gamma k. Since n is a unit vector, so cos square alpha plus cos square beta plus cos square gamma has to be 1. The magnitude of that is 1, and these are cosine angles. So this is just the direction of n. So alpha is the angle between n and the x-axis, beta is the angle between j and the n, and gamma is the angle between the third x-axis, z-axis and n. So if n is being represented like this, then I can write this as what would be dx. What would be dx? Dx would be k square by omega square mu dx. So this would be ex minus the x component of this. The x component of this, that would be how much? N dot E would remain like that, and the x component of n is cos alpha. Which is equal to k square by omega square mu. Now Ex, because we have already know that it can be written as dx by epsilon x, because dx is epsilon x into Ex, minus n dot E cos alpha, which is equal to k square. If I write this as, open this up, k square by omega square, and this will be dx by mu into epsilon x minus n dot E cos alpha divided by omega square mu into k square. Now omega by k is nothing but the velocity in the medium. Okay, so I'll write this as 1 by v square. So 1 by v square. But what is mu epsilon x? Mu epsilon x, because we know that the velocity is written as what? 1 by square root mu epsilon. Since this is the x direction, mu is the same in all the direction. So mu x would give us the velocity in the x direction. Velocity in the x direction. Similarly, Vy. So I can write this as omega by k square is 1 by v square. No issues. But mu epsilon x would be nothing but Vx square. So it would be Vx square into dx minus, this would be n dot E cos alpha omega square k square, again v square mu. So I can write this as dx, if I take this one this side, so dx common, you have 1 minus Vx square by v square equal to minus n dot E cos alpha by v square mu. So this would be dx v square minus Vx square is equal to minus n dot E cos alpha by mu. V square would get cancelled both the sides. Have this. So dx is now simple. It is minus n dot E cos alpha divided by v square minus Vx square, or n dot E cos alpha divided by Vx square minus v square. Similarly, we can the same way we can derive one dy. It would be, you can see that there will be no difference in the numerator. It would be same. Cos alpha will become cos beta, and then this would become Vy square minus v square. Similarly, dz would be equal to n dot E cos gamma divided by Vz square minus v square. So we have got dx this much, dy this much, dz. But we know that d and k, which means that d and n, they are perpendicular to each other, which means that d dot n must be equal to 0, which means that dx cos alpha, dx, and the x component of n is cos alpha, plus dy cos beta plus dz cos gamma, this should be equal to 0. And if you just see the values of dx, dy and dz, We can write this as n dot E cos alpha cos square alpha divided by Vx square minus V square plus n dot E cos square beta divided by V square minus Vy square minus V square plus n dot E cos square gamma divided by Vz square minus V square equal to 0. So n dot E can be cancelled out throughout, and you get the relation as cos square alpha by Vx square minus V square plus cos square beta Vy square minus V square plus cos square gamma Vz square minus V square equal to 0. This is standard equation that we were deriving. Basically, this is known as Fresnel's formula. In the next lecture, we will see that how we can derive the value of V from here in the case of uniaxial crystals, and how we get the solution as two different velocities in the same medium. Okay, there will be two different velocities of the electromagnetic wave in the same anisotropic medium. Thank you.